Hello everyone, and welcome back to Reverse Engineering Linux 32-bit Applications. In this video, we're going to continue our discussion of stack buffer overflows. So we've been talking about these for a little bit now. Now, in a previous video, we talked about something called return to libc. So the idea was this. I want to run some code, but I can't just call code on the stack because that's going to be a problem for me. The problem I'm going to run into is that the stack is not executable. So I can't just directly put my code on the stack, but what I can do is I can redirect things to some library functions. And libc is a great choice because most programs link with it. So, we talked about how you could do this and how you could call a function in libc last time. So in this video, I wanted to talk just very briefly about something called chained calls to return to libc. So what's the idea of this? The idea of this is that I need to call more than one function. Sometimes I can't just call a single function and do an exploit. I might have to call system. I might have to call exit. I might have to call something like set EUID that will set my effective user ID for a program if I'm trying to do some sort of privilege escalation. So there are many things that I might have to do that could require more than one function call. So I don't want to go too far down this rabbit hole, but I do want to make you aware of this process and sort of how it works. It can get kind of complicated, especially when you start getting into multiple function calls. Now, another reason you might want to use this particular technique. What if you have a parameter that's 0? So you have a parameter that's 0. Now you have a bit of a problem because you can't copy this onto the stack using stir copy or something similar. If you do that, then you're going to have a problem. Some other things that you might run into occasionally with this method. Sometimes the function that you are trying to call just so happens to have an address that contains 0 in one of its bytes, usually the last byte. So how are you going to deal with that? Well, the way you can deal with that situation is to call another function and use something like stir copy, or if that's the function that has the problem, you could use something equivalent like sprintf in order to call your method and get your null where you need it or avoid nulls. All right, so real simply, how does this work? Incidentally, there is an article in FRAC. If you're not familiar with FRAC, FRAC is an old school technology magazine, hacker magazine, whatever you want to call it. And this technique comes from issue 58.4. So let me just go ahead and bring that up for you real quick. So here is 58.4, and here is the article I'm talking about. It was written by a guy called Nurgle, and it goes through the classical return into libc that we talked about, and then they talk about two different techniques. One of them I'm not going to talk about here. It's called ESP lifting. You might say, well, why aren't you going to talk about it? Well, let me just scroll down here for you a little bit, and I will tell you why we're not talking about it. This requires that the binaries were compiled with this flag. So this flag being omit frame pointer. So I don't want to use something that relies on that, right? I don't want to use a method that requires that my programs were compiled with a certain flag. So instead, what we will talk about briefly is what is called the fake stack. So what is the fake stack, or frame faking as the author calls it here? Well, the idea is this. On the stack, you will have a frame pointer, your EBP, and then you will have some additional information that comes after. So you're going to have a return address, and then you're going to have some arguments. So here's sort of how this works. You have things that you've used to fill up your buffer. You calculated that offset, as we've talked about in previous videos. Then you have the address for your fake EBP0. So the first one, your first frame pointer. You can follow this with a leave return, sometimes just called a leave ret. So if I look at all of these functions, you'll notice that they have the same epilogue. Leave, what does leave do? Leave will clean up my stack, essentially. And then return. What does return do? Return goes to the address at the top of the stack, and that's where the function, or not the function, but that's where the program execution will continue. Can I find an address where there is a leave ret? Absolutely. They're all over the place. So all I need to do is find this address in my program. So this fake pointer points to my next fake pointer, and then I have another function, its address, something I want to call, a leave ret, and then any arguments for that function. And I can continue this on and on and on. So this is a very generic technique that I can use, and I can use this in order to call multiple functions in my standard libraries. You know, we say libc. It doesn't really have to be libc, but obviously it's a really good choice because it's probably there. So how would we implement this in practice? So I want to walk you through most of an example. Again, this can get very complicated, and you might have to call 7, 10 functions. It's really not clear sometimes how many you might have to call. I will say this is a pretty cool thing when you can get it to work. So if you can figure out a way that after calling 10 different functions, you can eventually ratchet your way up to root access, that's kind of cool. So let's go back here, and once again we will run our program. Let me run it up to our breakpoint and do some analysis as usual. And let me scroll down here just a little bit. And notice, of course, I have leave ret. Leave ret. So all of these functions are going to have a leave ret. Now, before we talked about ASLR and how this can be a problem for us. When we were talking about that, we mentioned that your program is always loaded in the same place. So that's the one saving grace in all of this. The libraries are randomized as to where they are, unless you've disabled it, as we have temporarily. And the stack is randomized. So now if I go to view memory regions, I'll notice that these things are all going to be in the same place every time. My stack's not executable, but here's where it is. And this is a nice thing. So how could I do this? Well, again, let me go to my command prompt. Let me open another command prompt. And let me go ahead and have a look at my library. So we said we're going to do read elf-s on lib32 libc s0. Let's see, so.6. And this gives us all of our different functions. So I could figure out the address for my function. And again, this is too much information. So I'm going to use something like grep to knock it down, which is what I did here. So let me go ahead and do that again. And that gave me my system address. So we noted this offset 3A940. And then we said, okay, there's system. What if I want to use stir copy? Stir copy is located at this address. Now, notice the address ends in 00. That is not good. This address ends in 00. That's a null byte. So I'm going to have a hard time putting that address onto my stack. So what's the solution? I just need to find something equivalent. What's equivalent? I could use sprintf, and this will accomplish the same thing. Now, it's a little bit more complicated to use, but it's still doable. So let me look for sprintf as an alternative. All right, so we're good. So I can see that sprintf has a different location that doesn't end in 00. So how could I use this? I could use this by noting where's my sprintf. So I'll just make a note to myself on a piece of scratch paper. By the way, when you're doing reverse engineering, don't underestimate having some scratch paper by your side. I know a lot of us, we're technical folks and we like to put everything on our computer, but it just takes too long to go back and forth and say, let me type this in over here. And it's just so much quicker to enter this stuff on a piece of paper. So it's 00049,080. Great. So that is sprintf and where it's located. So what could I do? I could use that address and make a call. I could build up this fake stack in order to chain together a bunch of function calls. Now you might say, I don't remember how to use sprintf. You could do a man on sprintf. And it comes up with man section 3, the programming section. And it will tell you how to use this function. What is the format string? How does that work? Etc., etc. So that is a little bit about sprintf. Going back here, I could say I want to be able to call to exit. And here's my function for exit. It's at 0002E7B0. So I'll go ahead and make a note of that. All right, so how could I use this? Now, I wanted to show you using testy, but you know what? I'm going to just copy this and make a new file. I'll paste it in this new file. I'm going to call chain.py. So I want to show you how does this work. So here I have my address. My address was F7E3B940. That was my address for system. So let me go ahead and just define a couple of parameters. I'm going to say system equals this address. And I'm feeling lazy, so I'm just going to copy it like this. So these are going to be addresses. All right, what next? Well, I have sprintf. So let me do a little bit of math here. Let me pull up my calculator. And I have sprintf is at 00049,080. To that, I want to add my libc. My libc started at F7 E0 1000. So this should be at F7 E4 A080. If my math is correct. I'll just go ahead and copy it from my cheat sheet. Sprint F is going to be at, and I have to convert it to little endin, so don't forget that part. 80 A0 E4 F7. And then finally exit. Where is exit? Exit is at the address of 000 to E7B0 plus F7 E01000. So that is at F7 E2 F7B0. Let me enter that here, and here's my exit. So I say exit is going to be here at, reversing at, B0, X, B0, X, F7, X, E2, X, F7. So now I have these guys. What do I need now? I need to find a leave ret. Well, that should be pretty easy to find. There's multiple ones. Let's use the one from right here. So leave ret is at 08048438. Oops, sorry. 8436. I was looking at the wrong line. That is my leave ret address for this one right here. There's more than one that I could use. So I can go back here and I can say leave ret equals, converting that to little endin, 36840408. All right, so now how can I run this? I can run this by building up this fake stack, this bunch of fake frames on my stack. There's only one thing left. And the one thing that's left is I need to find out what are my EBP addresses for the sequence. And I kind of have to go from there. So how do I find out these EBP sequences? Well, let me go ahead and go here. Go back to my debugger. And this is actually where I'm going to have my problem occur. So let me go ahead, put a breakpoint here. Let me run. And actually it was unhappy with me because I didn't send it the appropriate thing. I just used my little script in order to load this up, which is why my stack is not where I want it to be. Okay, so what's the next step? So let me go ahead and go back here to my testy script. I have my address for my system call, which I put in here, and let me make this a little bit different. Actually, I'm just going to do something a little simpler, and I am going to rerun this, because all I really want here is I want to know the address for the stack. So I'm going to run to my first breakpoint, do my analysis. Put my breakpoint here. Run to this breakpoint. We're still all good. I'm going to call stir copy. I've moved 1 to EAX. That's my return value. I'm getting ready to call leave. So before I call leave, my stack is at FF CF30. Another FF in there. That would help. When I call leave, that changes. And now my stack is at FFFFCF5C. Notice here's the return address that I pushed on the stack, and here is my argument, bash. So now if I call this next step, then I'm going to have some issues very soon. And here it's saying, hey, I got a signal from my child. So I used system to create a child process, but it didn't like running bash, basically, is what it's telling me. Okay, so now we have that address. So what do we do from there? From there, we can go back to our chain.py, and we can say, what is my address for fake EBP0? Well, that address is going to be, again, converting this to little endin, 5C, CF, FF, FF. So what do I need to do? I need to build this up. So how does it get built? It gets built like this. So up to this point, I'm just getting to where I need to inject things. And I'll get rid of this shell code because we're not really even doing any shell coding anymore. So anything I add to here is going to be my stuff. So I will say, all right, I'm going to add fake frame 0. So the first thing that's going to come is this. I'm going to say param plus equals FEBP0. So I've added that frame pointer. Next, I will add the leave ret. Remember what that's going to do. That's going to call leave, and it's going to call return. So I will call leave ret. Now what? Now I have to add in my additional calls. And here I have to do a little bit of math. So now I have to calculate my EBP1, my fake one. And so I have to add my EBP plus leave ret. And that is going to be that plus my argc. That's 4 bytes for each of those. 4 times 3 is 12. If I add 12 to 5c, I'm going to get what? If I was real lazy, I could use my calculator. And I could say, what is 5c plus c? And that is 6.8. So I could say, all right, this is going to be end in 6.8, xcf, xff, xff. So I'm going to have my first EBP, and then I'm going to have leave ret, and then I'm going to have my next EBP. And here I'm going to say param plus equals fake EBP1. So that's going to be the first thing that I add. And then I'm going to add my call. So let's just say I want to go to sprintf. Maybe that's where I'm going. Okay, so then I will say, all right, I will add my sprintf address. And then I have to add to that a leave ret and then any arguments. So I need to add any arguments to that function. So sprintf is going to want usually 3 arguments. You could have more than that. So I can go ahead and I can give it my different arguments. So what are some of those arguments going to be? Some of those arguments are going to be locations on the stack. Where on the stack will I be overriding these values? Again, if I want to insert a null, I have to use something like sprintf because I can't directly put a null on the stack using stir copy or something similar. So here's what I can do. I can use this and I can say, okay, here's my argument. My argument is going to be somewhere else on the stack. I'm going to go to, let's just, for sake of having something here, I'm going to say sprintf arg1 equals, and this is going to be my destination. And my destination is going to be on the stack. We'll just randomly say that it's going to be at F8, CF, FF, FF. So that is where I'm going to send something. What could be some of my other arguments? Well, I could say, all right, I need some additional arguments. I might have a second argument that is in my function, in my program space. So I could just say, all right, sprint f arg2 equals, and then something that would be in my program space would be something that starts with the hex value of 80, 080. So I could say, all right, I'm going to randomly say, here it is at F0X. And of course, you would want to look in your program and find something. 88X 04X08. And then you would have another argument to sprint F, a source argument, if you will. And that's probably something else on the stack. So for now, I'm just going to put something random in here. Let's say it's going to be F, C, CF, XFF, XFF. So the idea behind this technique is that you have to figure out this stack. And as you can see, if you're calling multiple functions, this gets complicated really fast. And you pretty much have to diagram all this stuff out. Right? You have to put it down on paper and say, look, okay, I'm going to call this function, which calls this function, which calls this function. What are all the arguments? How big are those arguments? And go from there. So you can do this, and the cool thing is that you can call functions like sprintf or strcpy if you're lucky that will allow you to insert nulls on that stack. Remember, whenever you call strcpy, if you don't overflow something, you're going to get a null byte at the end. So you can use this to actually zero out a location on the stack. So it's a very cool technique that you can do. Also things like if you want to set a user ID to root, that's 0. Once again, that's going to be problematic because you can't just use strcpy directly to put all this stuff on the stack. So, let me just finish out this frame to make sure that you guys understand how this works. So we have our leave-ret, and then we add our parameters. Sprintf arg1. Sprintf arg2. If I had an additional frame, what would I do? Well, I would take what I have here, and I'd do a little math, and I'd say I have 1, 2, 3, 4, 5, 6 things. I have 6 things here. They're all 4 bytes long. So I'm going to add hex 18 to this, and I will get my next value. So that is going to be hex 80 at the end. So my next fake EBP would be at this address. And how would that look? Fake frame 2, would start with the frame address, the EBP2, and then whatever function I'm calling, let's say it's printf again, leave ret, and then any arguments. All right, so full credit to the guy that, or gal, don't really know who, that came up with this technique. It's pretty cool, I think, actually. And as you can see, yeah, it can get really complicated. But sometimes that's what you have to do. Sometimes you find a flaw and you're like, all right, I can put some stuff on the stack. I can overflow something. Oh, the stack's not executable. Oops. What am I going to do? I'm going to do a return to libc. All right. Well, to really do anything useful, maybe I need to call a function that has a null in it, or maybe I need an argument that has a null byte in it, and that's problematic. So what can I do? I can do this. I can build my own fake stack, and from there, I can call multiple functions. So this is a pretty cool technique. There are some other ways that you can do this. Instead of using leave ret, there are some things that you can do where you do a pop, like a pop return instead. So this is not the only method that you can use. You can do a pop return, pop return. There are a couple of other things that you can do. Now, what's an advantage of using something like pop return instead of leave ret? Well, one big advantage is you don't have to calculate all these addresses for your EBPs, etc. You don't have to know where the stack is going to be exactly in memory. However, there are some other problems with that particular method. If you have null bytes, and that's part of the reason that you're using this technique, then the pop return isn't going to work for you. But this, again, was meant to be just an introduction to this technique. As you can see, these can get very, very complicated quickly. But it is something to think about. If you don't have an executable stack and you're trying to get around that, and you're thinking, well, what can I do? This is something you could try. You can try the regular return to libc, and if that's not enough for your purposes, you can chain all of this stuff together. All right, well, that's all that I wanted to cover in this video. Just as a reminder, this video is one in a family of courses here at Pen Tester Academy, your source for all things InfoSec. So I hope to see you soon back in this course or another fine course that we have here at Pen Tester Academy. So I'll see you then.